Let's see how transformations work with integration. We're given a transformation. T is given to be x equals 1/4 times the quantity of u plus v. Y is equal to 1/4 times the quantity of u minus 3v. The integral is the double integral over r of the quantity 4x plus 8y dA, and r is the parallelogram with vertices -1, 3, 1, -3, 3, -1, and 1, 5. Now it's important to note here that r is a region in the xy plane. So when we look at the vertices of the parallelogram, we're actually looking at the edges of the parallelogram, and we're going to come up with relationships that involve x's and y's. Separate from that, we need to take the transformation, which has x in terms of u and v and y in terms of u and v, and we need to solve them for u, and u will be a function of x and y, and v, which will be v as a function of x and y. And that's going to be the inverse transformation. I'll tell you what we'll do with them after we've done both of those things. It wouldn't make any sense now. I'm not sure how much sense it's going to make ever, but we're going to give it a shot. Let's first look at the region R in the xy plane. Here's our region R in the xy plane. It's a parallelogram, which means it's got two pairs of parallel sides. Let's use some colors to identify the parallel sides. I know you can see them, but I'm doing this for a reason. And I will let you verify that the sides that are more vertical than horizontal, the ones I've labeled in green, have equations y equals -3x and y equals -3x plus 8. The other two sides that connect -1, 3 to 1, 5 and 1, -3 to 3, -1, I have in purple, and I will let you verify that they have equations y is equal to x plus 4 and y is equal to x minus 4. We can rewrite the green equations as 3x plus y equals 0 and 3x plus y equals 8, and the purple ones as x minus y equals -4 and x minus y equals 4. For right now, let's say I did that just so we could have in all equations here x and y on the same side of an equation. Now we've done all we're going to do with this region R and its equations. Let's come back over here and the idea that we need the inverse transformation T inverse. We need to solve these equations for u and v in terms of x and y. So I'm first going to start with x equals 1/4 times the quantity of u plus v. I'll call that equation 1. And clearing the fraction, we get that 4x is equal to u plus v. The equation y equals 1/4 times the quantity of u minus 3v, I'll call that equation 2. And clearing that fraction gives us 4y is equal to u minus 3v. If I eliminate v from this system, I can solve for u in terms of x and y. And since that's what we want, that's what we're doing. To eliminate v, we're going to take 3 times equation 1 and add to it equation 2. So 3 times equation 1 gives us 12x equals 3u plus 3v. Add that to equation 2, which is 4y equals u minus 3v. The 3v's subtract out. We have 12x plus 4y is equal to 4u. That simplifies to u equals 3x plus y. Now we can turn around and take the same two equations, 1 and 2, and eliminate u. In order to do that, we're going to take equation 1 and subtract equation 2 from it. 4x equals u plus v. Negative 4y equals -u plus 3v. Adding those together, we get 4x minus 4y is equal to 4v, and so v is equal to x minus y. Now folks, check this out, and this is what the transformation was designed for. Over on the right, when we developed our green equations, we had 3x plus y equals 0 and 3x plus y equals 8. Now we have that 3x plus y is equal to u. that means that u must go from 0 to 8. For the purple equations, we had x minus y equals -4 and x minus y equals 4, and lo and behold, v is equal to x minus y. Putting that together, we see that v goes from -4 to 4. We were able to use the region together with the inverse transformation to find our limits of integration. Now what we need to do is go back to the original transformation so that we can find the Jacobian of x and y in terms of u and v. And we know we need the original transformation because when we write down what the Jacobian looks like, the u and v are in the bottom, and if you think about dy dx, x is in the bottom, that's your independent variable or your input variable. We also need this transformation that was given to us in order to substitute for the integrand, right? 4x plus 8y, we need to use the expressions for x and y in terms of u and v. The Jacobian is showing up in our dA. So let's get to that Jacobian. The Jacobian of x and y with respect to u and v is equal to the partial of x with respect to u, the partial of y with respect to u, the partial of x with respect to v, the partial of y with respect to v. Looking at our transformation, the partial of x with respect to u is going to be 1/4 because x is 1/4 times the quantity of u plus v. The partial of y with respect to u, well, y is 1/4 of the quantity of u minus 3v, and so it's also 1/4. The partial of x with respect to v is going to be 1/4. The partial of y with respect to v is going to be -3/4. Evaluating this determinant, we get -3/16 minus 1/16, which is -1/4. dA can't be negative, no worries. We actually need the absolute value of the Jacobian. We can now say the double integral over r of 4x plus 8y dA is equal to the integral from -4 to 4, those are the limits on v, of the integral from 0 to 8, those are the limits on u, of 4x, but x is 1/4 times the quantity of u plus v, so 4x is simply u plus v, plus 8y, but y is 1/4 times the quantity of u minus 3v, and so 8y is going to be 2 times the quantity of u minus 3v. All of that times the absolute value of the Jacobian, which is the absolute value of -1/4, times duv dv, and I picked the order du dv, essentially when I said that the first integral went from -4 to 4. At this point, the integrand just requires us to collect like terms, and then the integral requires us to use the power rule. I'm going to jump ahead and let you verify that the answer here is 192.